So apparently I got a little bit overzealous in a previous video when I was talking to you all about using the periodic table to work out electron configurations, because some of that is actually talked about here. There is some new stuff here that I'm going to go over as well, but some of this I'm going to skim through pretty quickly because we've actually already talked about it. But the very first topic on this page here is actually a new thing we have not seen yet. So the very first point here, the group number corresponds to the number of valence electrons. This is actually incredibly handy. If you don't want to have to do what we just did in the last video, which is write out the whole electron configuration to figure out how many valence electrons you have, what you can do instead is look at the group number for at least the main groups. For the transition metals, this doesn't work, but for the main groups, if you're using the 1A, 2A, 3A, 4A naming method, the number of valence electrons corresponds to the number. So everything in this column has one valence electron. Everything in this column has two valence electrons. Everything in this column has three valence electrons. Everything in this one has 4, 5, 6, 7, and 8 valence electrons, which is, again, incredibly handy if you're trying to figure out how many valence electrons something has. If I say, how many valence electrons does phosphorus have? Well, you don't have to write out the entire electron configuration for phosphorus. You can just say, where is phosphorus? There it is. It's in column 5A. It has 5 valence electrons. Or I guess if you wanted to use the new numbering, it's in column 15, and so the second number there, the 5, tells you how many valence electrons that element has. So that is incredibly useful. It'll save you a bunch of time, not having to write out the electron configuration every single time you want to figure out how many valence electrons you have, which we will be doing a lot when we get to Lewis structures. It is completely based on how many valence electrons an element has. And so it's very handy to just be able to look at where it is on the table and say, oh, it has this many valence electrons. The other two things here we've actually already discussed. So the length of each block is the maximum number of electrons a sublevel can hold. So this block here, this is the S block, the D block, the P block, and then the F block. So we have 2, 10, 6, and 14 elements wide here, respectively, because of the number of orbitals, which then governs how many electrons it can have. But like I said, we discussed that in a previous video. And the same thing here, the period number corresponds to the principal energy level of the valence electrons. So if you have an element on the 5th row, its valence electrons are going to be in the 5s and the 5p. So the period number corresponds to the principal shell of the valence electrons. And so we can see that here. This particular graphic here is just showing the valence electrons. It's not showing you the core electrons, and so see here as you go from sodium over to argon, you're just adding in electrons to those 3s and 3p sublevels. When you start looking at valence electrons, or just the outermost electrons for all of the elements, for the most part they do follow the rules we've talked about up to this point. It's like if you take a look in the P block here, it is very, very consistent. So as you go down the halogens, for example, it is just the period number S2P5. So 2S2, 2P5, 3S2, 3P5, 4S2, 3P5. It's very, very consistent, the electron configurations. But if you notice here in the transition metals, in the D block, while there are some that are consistent, there are quite a few that have really odd electron configurations. So for example here, palladium doesn't even have any electrons in the 5s. It has 4d10. when it should, based on our rules, be 5s2 4d8. So it's essentially stolen the 2 electrons out of the 5s and put them into the 4d. And there's lots of examples of things like that here in the transition metals. These irregular electron configurations, as we call them, usually crop up because it is energetically favorable to have in the D sublevel here. So this is what the say we have the 3D here, for example. We have 5 orbitals available in the 3D, and it is energetically favorable to either have it half full, so to have 1 electron in each of those orbitals, that is energetically stable, or to have it completely full. One or the other is more stable than having it 1 off or 2 off from being full or half full. And so sometimes you will see irregular configurations where it will pull electrons one way or another to get that half full or completely full configuration. This doesn't always happen, but it is a fairly regular thing. So it's like you can see here, it pulled one of the electrons from the 5s up to give you 4d5 here with molybdenum. But then it puts it back when you get to technetium. So you don't have 5s1, 4d6. So it's trying to maintain that 4d5. So that's the most common thing that you see with these. Thankfully for you, I do not expect you to have these irregular configurations memorized, because you would essentially just have to have them memorized, because it's even the irregularities are not regular. So you can see, like here, for example, chromium, it pulls 1 electron out of the s orbital up to give a half full d. Same thing with molybdenum. But then when you get to tungsten, it doesn't do it. And I forget what dB stands for, but that one is even stranger. And so they're not regular in their regular in their irregularities. So I'm not going to have you memorizing these. It's more just I would like you to be aware that they exist. And so you can see some more examples here. So ruthenium, this is what you would expect to see based on our rules, 5s2 4d6, but ruthenium in reality is 5s1 4d7. I'm actually really not entirely sure why it really wants to have 4d7, but that is what you find experimentally. If you actually go out and do an experiment, you will see that this is the ground state for ruthenium. But most of the rest of these exceptions here, you can see how they're trying to get either D5 or D10, because that is favorable. All right, so I think we're going to go ahead and call it here for this video. It'll be a relatively short video, because the next big topic here is periodic trends, and I think I don't want to jump into that just in the last few minutes of the video. So we'll pick up in the next video talking about periodic trends, different properties, both chemical and physical properties, that vary from one side of the periodic table to the other, and going up and down the periodic table. It will vary. So we will talk about that in the next video.